And I'm going to be talking about the bomb calorimeter report. Okay, first, a little introduction on bomb calorimeter. We used a bar oxygen bomb calorimeter. This accurately measures the heat release from combustion of a liquid or solid fuel sample. The bomb is going to be submerged in water, which is conductive, and that way we can measure the rise of heat from the water using a thermocouple. And this is widely used and considered standard for many of the practices to get accurate measurements of heat provided. A little bit of the objectives that we're going to try and accomplish. We want to familiar ourselves with the principles, procedures, and the analysis techniques. We're going to want to determine the thermal capacitance of the calorimeter itself and determine the heating values of 3 different fuels that we're going to use to test in the test. The theory behind the bomb calorimeter is quite simple. It's the first law of thermodynamics, just Q equals mCv delta T, where Q is your heat of combustion and delta T is the change in temperature of the water. And then your MC is going to be the thermal capacitance of the calorimeter. And this is also equal to the heat of combustion over delta T. So that way, if we find the heat, the amount of temperature that the water is raised from the bomb, then we can find out the thermal capacitance of the calorimeter. So the first thing we did to do the experiment, is we weighed a particular fuel to get that in grams. And then we cut the wire, ignition wire from the bomb, which you can see here, at 10 centimeters. And then we attach that to the fuel sample and the electrodes, and there's going to be a circuit running through here. You place the lid on the bomb, and you pressurize the bomb with oxygen, making sure that you get as much oxygen as there is possible by filling up with oxygen, depressurizing it, and filling it up again. And then we're going to have 2 kilograms of water in the stainless steel container so that can detect the change in temperature. Then you want to attach the thermocouple, lower the bomb carefully into the water, connect your electrical lead to the bomb and the terminal. Then we have a stir to make sure that the water is at a steady state, the temperature is evenly distributed throughout the water. And we're going to ignite the fuel and record an initial and final temperature reading. And then once we're done recording the temperature, we're going to take the initial wire out, measure that to see how much heat was put into by the ignition wire. So this is the results. Our first fuel was benzoic acid. We had 1.02 grams of that. And this is our temperature versus time graph. And you can see we went from about 23 to maybe a little over 25 degrees Celsius, giving us a delta T of 2.55 degrees Celsius. The next fuel we did was just a peanut, measured at exactly 1 gram. And the same thing here, went from around 25 to a little over 28, roughly giving us a delta T of 2.8 degrees Celsius. And the third was a shopper candy, which gave at a mass of 1.06 grams. And this gave us a delta T of 1.48 degrees Celsius. So first we can calculate the thermal capacitance of the calorimeter. And this is just the thermal capacitance of the devices itself, which would be the sum of specific heat times the mass. So the 2 main things that we want to use, that we want to get here is the stainless steel, the mass and the specific heat of stainless steel, and the mass and specific heat of water. We had 3,000 grams of stainless steel and 2,000 grams of water, multiplied by their respective specific heats, and it gave us thermal capacitance of 2,360 calories per degree Celsius. Knowing that, we can find the heating value for our unknown samples, given this equation here, by multiplying total capacitance times delta T, and then subtracting out the heat that was added by the ignition wire. As you can see here, we found the benzoic acid gave us a heating value of a little over 6,000 calories. And so then, you divide that by your mass to get the heating value to do just under 6,000 calories. Same thing here with the peanut and the shocker. So compare this to other heating values. I just took butane and looked that up, which gave us around 12,000 calories per gram. And comparing to 5 other samples, I got a mean for benzoic acid of a little over 6,000 calories per gram. Give us a standard deviation of that, and your accepted value of your heating value of benzoic acid is 6,318 calories per gram. So we were a little bit off here. As you can see, we were a little under 6,000. It could be due to many just factors in the experiment, errors in the experiment. So that's it. Any questions?
What is the stir affect the temperature of the water?
Yeah, it's supposed to make sure that the water is at a steady temperature throughout the whole container, so that's not going to